that the components of the velocity, that is energy levels, how it will be in case of a turbine, how in case of a compressor. If you look at it, so if I take for a compressor, what will happen? I'm trying to show the size of the energy, that is in terms of velocity. If I call this actually, if I call this as relative velocity, VR1, okay. If I call that as a relative velocity, that is the relative velocity is the velocity with which the fluid is flowing. So what will happen in case of a compressor or a pump actually, the fluid enters at the lower velocity or lower energy levels and it goes at higher energy levels. That we call it as VR2. Okay, that means there is an increase in the energy levels or the velocities. And also you can see that what is this plus actually? This is my pressure side of your vane or blade, and the negative, this is my what we call it as pressure side, and this is your suction side of your blade. So what's happening here actually? The fluid is gaining the energy. The fluid is gaining the energy in case of a your compressor or a pump or anything. But when we come to the turbine on the right hand side, the fluid already enters at higher energy. That means VR1 in case of a compressor is less than the VR1 what in case of a turbine. Okay. Now, where the exit, the VR2 is at the, that means it's going to give the energy to the rotor. Give the energy to the rotor so that it goes at lower energy. Now, if you look at it, I do have the pressure side inside because it's pushing, and this is my suction side. This is a simple explanation what we can give to understand how the component of energy, how the components of energy levels will increase in case of a compressor or a pump, or it will decrease in case of a turbine, whatever. Now, moving further, as I told that we have three major components of velocity. One is the absolute velocity component. The other one is your peripheral velocity component or blade velocity. And the third one is the relative velocity of your fluid. So these are the three major components of your whenever we try to analyze your turbo machine. Now let us look into two types of machines. One is the radial flow machines as well as the axial flow machine. Now if I take the radial flow machines, okay, it's also called as radial flow compressor or whatever it may be, radial flow machines. It's also called as centrifugal flow machines. Now, if I try to look into this, this is a simple schematic what I have. So radial flow machines, why it is called radial flow? Because the flow is in the radial direction. The flow is in the radial direction. That means if suppose this is my axis, see this is the axis, this is my axis, and this is exactly the radius. Okay, this is the radius. So the flow is in the radial direction. So flow can go outside or flow can come inside. Okay. Now if I take the compressor or whatever it may be, what will happen? What is the main purpose of your compressor or whatever it may be? It is to increase the energy. That means the flow enters here and it exits outside here. This is my out, this is my in. But if I come to the turbine, the flow enters at the outside and this becomes my out actually. This is a major difference between your compressor and a turbine when I consider the radial flow machines. The flow enters at the inside, that is we call it as a hub or eye of the impeller, and flow is going out. That is, it's going to gain the energy in case of a pump or a compressor in the radial flow machine, and in case of a turbine, the flow enters, that means higher energy fluid enters the outer radius, and the outer radius, we call it a tip actually, and it comes in, it loses the energy, it goes inside, that means at the hub actually. Okay, this is my axis, whatever it may be. Now, if I if I try to draw the velocity triangle and try to analyze this machine, actually, I'm trying to put these two circles. Okay, I'm trying to put these two circles and try to see it. Actually. So what are these? To analyze this. Okay, let's try to analyze this. So now, if I try to look into this, actually, this is my hub, and sorry, this is the tip actually outside. This is the tip, and the inside one is my hub. So even for a turbine also, this is my hub, this is my tip. Tip is always the outer radius. The outer radius is tip, and inside radius is the hub actually. Now I need to draw what do we call it as a vane or blade. So if I try to draw a vane or blade for this kind of a situation, and this blade has to be such that this blades will clearly show the fluid has to flow in between that. Let me draw two blades actually. Let me draw two blades of certain curvature. Let me draw two blades. Okay. This is for your maybe compressor. Now, in compressor, what will happen? The fluid is flowing from inside to outside. Okay. If that is the case, what will happen? The fluid will enter at some velocity. The fluid will enter at some velocity v1. So if I try to draw the triangle at this particular point, so some velocity. This is my. It represents the quantity and the magnitude. If I tell, say for example, this is the velocity with which your u1. Why it is called u1? It is pi d1. So this is my d1. This is my d1. This is my d2. Okay. My inside diameter is less than the outside diameter. Now at the same time, I have one more velocity. What is that actually? It is a relative velocity, and this relative velocity is always in the direction of your vane. So that means it will be in this direction. It is always with reference with respect to the blade. This is my VR1. That's always, it makes an angle with respect to, see, it makes an angle with respect to beta. We call that as C. We have what is called as beta angle. That is blade angle. So if I have something like this, okay. I try to measure beta. So beta is my blade angle. So with respect to the relative velocity. So always the relative velocity is with respect to your blade angle. Okay. So this is the convention what we use it actually. Equal to that. So this is my VR1. So that I will be able to get a velocity triangle at the inlet. This is how you are going to put the velocity triangle. I can draw a similar velocity triangle, and so this is my 1. So 1 is the inlet. So this is my 1. See, I have put the U. See, what is the U actually? If this is my hub, and I'm trying to put this is the tangent actually. This is my tangent representing the U1. That means your turbo machine is also rotating in the same direction. That means for compressors or a pump, I go with the convention that it's rotating in clockwise direction. Direction like this. It has to go in the same direction as that of your blade. See, it has to go in the same direction as that of your blade. Look at this. This is my VR2. So VR2 represents the relative velocity of the fluid going out. It makes an angle of beta, what I told once again. So this is my outside tip actually. This is my blade. It goes out like this. It makes an angle of beta 2. That means this is with respect to because I do have a bigger diameter. Okay. What will happen to the fluid? See, at the same time, it has to go to the next machine or something, whatever it may be, next set of blades or something. It has to go with a V2 velocity. That is your absolute velocity. So it will be a bigger one in case of compressor. So I'll be getting your VR2 will be bigger, and V2 also will be bigger, and U2 will be bigger. So I'll be getting something like this. So this will be my V2. So if I call this as V2, okay, just I'm trying to show here. Now if I try to, so U2 is the bigger one. So U2 is the bigger one. Now if I try to join this, this will be my U2. So this is, I am having a bigger U2. So now if I am trying to construct a triangle at the exit, this is how I am trying to construct the exit velocity triangle. So I have, say, three major components. What are the components? Absolute velocity, your peripheral or blade velocity, and your relative velocity. So it makes an angle of, see, I can draw the corresponding angles to it. Alphas, your betas, all those things I can draw. Fine. Otherwise, if I want, I can move this V2 also. See, I can draw the same thing. Instead of drawing like this, I can draw my V2 to over here also. Doesn't matter. So that V2, so that I can get a triangle like this. So instead of this thing, instead of drawing in this fashion, I can draw like this also. Only V2 I am going to make so that I can get the velocity. So whatever the way I can draw the velocity triangle, ensuring that I am going to get a vector addition or a vector principles velocity triangle. This is how it is drawn. So inlet triangle at 1 and exit triangle at so. Now if you closely observe, the velocity triangle at the exit is bigger compared to the velocity triangle smaller because of, say, I am not drawn to the scale. I am just trying to explain you. But when I draw to the numbers, that is, it enters at 50 meters per second, exits of some 80 meters per second. Okay, or the inner diameter is maybe 30 mm, the outer diameter is 60 mm. So when I try to go, speed is around 3000 rpm. When I try to calculate and put the numbers and try to explain, so it shows that my velocity triangle at the inlet and velocity triangle at the exit, they are different. So for a compressor or a pump, the velocity triangle at the exit is always bigger. It shows clearly the higher energy level. So even in your examination or when you're trying to solve the problem, this thumb rule has to be remembered. Now let us come to the turbine. So now when I come to the turbine, what will happen? Same thing. Let me draw the triangle for that also. Okay. Let me draw like this. Okay. This is my, in this direction. Sorry. I'm just rough diagram I'm trying to draw. Okay. Now what will happen here actually? Here the fluid is entering from outside. See, the fluid is entering in from outside. So the fluid enters with some velocity v. Okay. Let me draw with respect to this. It enters with some velocity v1. So let me take this as v1. Okay. And I do have the tangential velocity at the outlet. This is 1. So if you look at it, 1 is the inlet to the turbine and 2 is the outlet to the turbine. Okay. 1 is the inlet. So inlet velocity triangle, what I am trying to draw. Now if I try to look at the tangential this thing, so this will be always tangent to this. This will be my bigger one. I can go in this direction. I call this as, so this is in this direction. So this will be, the rotation will be in opposite direction. Okay. Now what will be the direction of your VR? See, this is my, see, VR. So VR will be in the direction of your fluid. So this will be my VR. So this will be my VR. Okay. VR1. Okay, this will be my VR1. So now I can, if I want to draw the velocity triangle, I can do that. So I can just move this V1 over here, U1 over here, and VR1. I can draw parallel to this VR1 what I already have drawn. So I'll be able to get my VR1. So this is making an angle of beta 1. See this. This is where I have the beta. If it's at the inlet, it's beta 1. So beta 1 represents the inlet, actually 2 represents the outlet. I'm going with the same sign convention. So I'm able to draw the, so now here what's happening? The fluid is trying to push your machine. So this will be the direction of rotation. The fluid is pushed. The fluid is pushing your rotor, so it's moving in this direction. Now similarly, what will happen to your exit velocity triangle? I can go by the same logic. It goes in this direction. So this is my VR2, fine, and I do have the blade velocity, which is exactly in this direction. Okay, it's a smaller one. It is V2, U2. Okay, and where is your V2? V2 will be smaller. So V2 will be much smaller compared to this actually. So V2 also will be going in this direction. So I don't know what the direction it's going in. So this will be my V2. So if I draw to the scale with number, then I'll be getting it. So if I try to combine this U2 over here and try to draw this will be my U2. So now if you closely observe, my inlet velocity triangle is bigger and your exit velocity triangle is smaller in case of a turbine. So this is for a compressor or a pump. This is for a turbine, what we call it. These are the radial flow machines. Okay. Now we do have other kind of a machine, that is axial flow machines. Now maybe whatever I shown, no, the same thing is shown here. You can look at this. This is what is there in most of the textbooks. So the black one represents the direction of rotation here. This is what a filled arrow. This is an empty arrow or non-filled arrow. So that clearly shows with the angles beta 1, beta 2, everything is shown. So these are taken from Bhaskaran, book Bhaskaran. So it's clearly shown. Now, when you come to the axial flow machines, so we call it as axial flow machine. Okay. In axial flow machine, what will happen? Your direction of the fluid, actually, the direction of the flow is in parallel. So this is my axis. This is my flow direction. Okay. This is also an axis, and this is the direction of the flow. Now, for a pump and compressor, what will happen here? Look at this. See, the fluid will enter here and exit. See, fluid enters at 1, it exits at 2. So what will happen in case of a turbine? Fluid enters at from higher pressure and it exits at 2. So I clearly shown the corresponding blades here, which are self-explanatory. 1 to 2, 2 to 2. So 1 to 2 from inlet. So this is the direction of fluid. Here, what will happen in case of pump and compressor? The blades are transferring energy to the fluid and fluid is thrown out. But in case of a turbine, the fluid will be pushing your blades. The fluid will be pushing your blades, and this is how what I'm going to get. So what are I shown the type of blades? No, this is how the blade. See, this is my leading edge. This is my trailing edge. So this is my leading edge. This is my trailing edge. So same rule of principle can be applied even for radial flow machines. Fluid enters at the leading edge. Fluid exits at the trailing edge. The fluid enters at the leading edge in case of a turbine and trailing edge. The difference here is, here the pressure is low, here the pressure is high. Here the pressure is high, here the pressure is low. So in case of a turbine, the expansion of the fluid takes place, and in case of a compressor, the compression of the fluid takes place. That's a major difference. Now, when you have such machines, actually axial flow machines, how to draw the velocity triangle? Let me teach you. Now, so when you have such machines, what will happen? So usually we try to draw the open. That means I'm going to open the blades like this. You need not draw the full blade actually. You need not draw the full blade shape of the blade, and just a curves are is sufficient. So this is how the curves look like. Okay, this is how the curves look like. The only thing is difference between your turbine and your pump is, so say for example, this is for a compressor or a pump. If I try to do this is for a compressor or something, what will happen here actually? The fluid is pushing your blade. What will happen? The fluid enters. Suppose this is my 1. So this is my 1, this is the 1, and this is 2. And in case of your turbine, this is 1 and this is 2. Let me draw the triangle for it actually. Now for 1 and 2, what will happen? The fluid enters at some velocity. So let me call it is entering axially. We call it as axial flow. That means what's happening? It will be entering like this. That means it will be exactly making an angle of alpha is equal to 90. That's the meaning of it. This is how it enters. So this is my V1. So what happened to your VR? So VR is always it is in the direction of your VR is always in the direction of your blade. It makes an angle of, see, what is it actually? This is my blade angle, beta. It's at 1, I call it as beta 1. Okay. Now, when you have this particular, what will be the direction of your U? So this is actually pushing in this direction. So that means this is my, these are my suction sides, these are my pressure side. So this has to move in this direction. If that is the case, then my U will be in this direction. Okay, my U will be in this direction, U1. So if I want to construct a triangle, so I will write it over here, and this is my U1. This is my inlet velocity triangle for a compressor or a pump. Now the fluid is flowing like this. The fluid is flowing like this. The fluid has to enter from inside to outside. Okay, the fluid has to enter from inside, it has to go out. So now it has to go out. So what the direction? So it has to take the direction. Okay, now it will take a direction. See, suppose this is my direction it's going. So it has to go with higher energy. So this will be my VR2. And what is the angle it's going to make? See, it's going to make the angle based on your beta 2. Beta 2 maybe 90 degrees, 85 degrees, 75 degrees. Fine. It goes, that means if I try to take it from inside, it's only my beta. Fine. I'll show this actually. Now, this is the angle with which it's going to go. What is the direction of your U? See, here in case of axial flow machine, your U1 and U2 both are same because you have this mean diameter. The diameter remains same. So U1 and your U2, so U1 is equal to U2. So here also my U2 will be in the same direction. This will be my U2. This is in the same direction. This is my U2. Where is my V? That means my V2 will be in this direction. I don't know the angle, so I can find it. This is my V2. I can push it over here and try to parallel to this particular thing, to this particular. Okay. So just I'm not drawing to the scale. That's why I'm getting like this. If I draw to the scale, then it will be like this. So then this will be my V2. Okay, so I got the exit velocity triangle for an axial flow machine. What about for an turbine? So this is for a compressor. See, this is for a compressor. What about for a turbine? A turbine, it looks something like this. This is for compressor or a pump, same thing. Only thing is the numbers may change. That's it, the numbers may change. Your type of how you are going to draw the velocity triangle, methodology remains the same. So what will happen in case of your turbine? The fluid enters at some velocity. So let the fluid enters at a bigger velocity. This is the direction of, maybe it enters like this. So this is my V1. Okay. Now what will happen here actually? Here, as I told, the fluid will be pushing in this direction. So fluid will be in this direction, it will be pushed like this. So I do have the pressure side here and my suction side here. So what will be the direction of your blade? So blades will be moving in this direction. This will be my U1. And where is my VR1? So VR1 will be actually, this will be a tangent to this. This will be almost like this, in this direction, to the your blade. Actually, this will be a tangent to your blade. And what is the angle it's going to make? It say if the so this is my beta, so it makes an angle of same thing here, beta 1. So if it is at inlet, it will be beta 1. So this is my VR1. So now I can push this V1 and based on the size of my V1, so U1 just like this, I can construct my velocity triangle here. This is my V1. Okay. Now the fluid is flowing in this direction. So the fluid is flowing in this direction. So if I want to draw the exit velocity triangle, it will be like this. So it will be a smaller one because angle VR2. So this is my beta 2. This is my beta 2. It makes an angle same way angle. So what is my U1? See, U1 and U2 both are same here. U1 and U2 both are same. So this will be my your U2 or whatever it may be. Then it goes out with a velocity. See, this goes out with a velocity like this. So this will be my, or it will be going somewhere like this, or sometimes it may be going exit axially like this. Whatever it may be. It may be like this also. And I'm just giving different conditions. Now, depending upon that, I can complete my velocity triangle like this. So this will be my machine. Okay, now we learned that how we can draw the velocity triangle for a radial flow machine and for an axial flow machine. Once you have this actually, so I can draw this velocity triangle and clearly show the triangle on the meridional plane. Okay, so where exactly is my meridional plane for an axial flow machine and where is the meridional plane on the your radial flow machine? That already we have seen that in the previous class. So we need to draw this velocity. So velocity triangles clearly show the energy levels of it. Okay, so now when I try to simply say, for example, if I try to combine this and try to draw the velocity triangle at the inlet. Okay, how usually we try to draw actually? We don't put the complete 360 degrees. We will try to put one, say for example, this is my hub, sorry, this is my tip and this is my hub. Okay, this will put only one blade we'll try to put. Okay, we'll try to put this one blade and we'll try to draw the triangle for this. Okay, now if I try to draw the velocity triangle for a pump or a compressor at inlet, whatever it may be, so it looks something like this. Okay, and this velocity triangles at the inlet or exit, it looks something like this. So now it ends at the velocity V1. Okay, I'm trying to draw bigger triangles. So this is my V1 and this is my VR1, whatever it may be. Okay, and I do have my U1 like this. Okay, because this is for a pump or a compressor. Now I need to show the exit velocity triangle. So what I'm going to do actually, I will draw the velocity triangle at the exit. So goes like this. Fine. And this being a bigger triangle at the exit, I can put it like this. My U2 and this is my V2 and this is my VR2. So this is the direction of rotation, whatever it may be, this all will show. Now we need to show the angles actually. As I told, the fluid is entering with the flow angle. Fluid is entering with respect to flow angles. So what are the flow angles? Flow angles is nothing but see, that is nothing but I do have a nozzle or something. Okay, nozzle which will be taking the fluid or it is entering, or I'll be having some kind of a sump or something, whatever it may be, of a compressor. It will be entering at some angle. So that needs some reference actually. So usually this reference is taken, see, this reference is always with respect to a tangent. That means where is this U1? Where is my u1 is coming? U1 is written like this. It is a tangent. Look at this. U1 is always with respect to tangent. So now, always with respect to even beta. Beta is also, see if I try to write here. So this is my beta 1. So your alpha 1 and beta 1 are with respect to some reference, that is with respect to tangent, that is your u. So similarly, I can have alpha 2 and your beta. I can have my alpha 2 and your beta 2. So once again, your alphas and betas are reference to your tangential flow velocity, or your what we call it the blade velocities. So when you are trying to draw the velocity triangle, this is how you are supposed to do. So in the problem statement, they can give fluid intercept. In case of a compressor, so fluid intercept 10 meters per second with a flow angle of 15 degrees. And the blade angle at the inlet is found to be maybe 35 degrees. If that's the case, I should be able to draw the inlet velocity triangles. Now, if you look at it actually, what is my V1? V1 is my, what is it actually? It is the axial, what we call it as absolute velocity. It is the absolute velocity. And what is the unit actually? It is meters per second. Okay. What is my U1? Now, a similar thing at the outlet. So if that is V2 is the, once again the absolute velocity in meters per second. What is my U2? It is the tangential velocity or blade velocity. Once again, unit is meters per second, and your VR2 is equal to the relative velocity in meters per second. This is at the outlet or exit. The same the only thing is it will be in the reverse direction. That's it. Now, as I told that, you have see this is my component of velocity. So I will take this velocity, whatever I have. So this, I will take this velocity. Velocity, whatever I have, I want to take this. Okay. Now, once the velocity I have, make it a little big. Okay. So this is the velocity, whatever I have. Okay. As I told, you have this v component. See, this is my v component of velocity. What is it actually? This is your absolute velocity component. I can resolve this. It makes an angle of alpha. Let me take this. Okay. Taking only the. Okay. Now, I have this actually. So it makes an angle of alpha. I do have what is called as, see, this is, I call it as VW1. That is your tangential component of the velocity, or it's also called as peripheral velocity component of this velocity using the trigonometric principles. Then what will be your VW1? So if I go and call cos alpha 1, what it is actually? It is VW1 by V1, or your VW1 is equal to V1 cos alpha 1. That means I have the absolute velocity component, take cos of it. So cos alpha 1, I'll be getting what is called as VW1. So VW1 is my, it's called as tangential, okay, or it's also called as peripheral. It's also called as tangential or peripheral, or few books they call it as whirl component. Why it is actually? Because you see this, see the direction of this u. U is tangent, and it is also your radius. Sometimes it will be peripheral on the outer radius. Or what is whirl actually? Whirl is something, but it's going to give some kind of what is called as a torque. So the component of velocity which is go in merge with respect to your u1 is called as a vw1. And there is another component of velocity which is your b sine alpha 1. Okay. Then what is this vf1? And I just trying to explain with respect to a triangle. So vf1 is nothing but it is also called as flow or meridional. Why the meridional? Hope you remember in my first class, I did one I had a meridional axis which was vertical. I did a circular projection, whatever it may be, projection on it actually. So flow means it can be an axial or whatever it may be in the axial flow machines. So flow component or the meridional component of your absolute velocity. So now, if I try to superimpose this actually on this particular, you already have velocity triangle. So I can, so this will be my VF1 and this will be my VW1. Okay, I am trying to superimpose so that the components of velocity on the earlier existing the velocity component. That means now total how many velocity components I have? I have one absolute component V1 with the absolute velocity and its two components VW1 and VF1, and I have my your peripheral velocity, your blade velocity. Then I have my relative component. So there are totally this many components of velocities in your velocity triangle. Then what is my alpha? See, alpha is the flow angle. If I try to look into this actually, alpha is the flow angle measured with respect to the tangent, and it's measured in degrees. Okay. Then what is my beta? Beta is the blade or vane angle measured in degrees with respect to the tangent to the maybe at the hub or tip axis. Okay. So now when we are trying to measure these components of velocity, so I can clearly tell that what type of machine I am trying to look into that. Now, when you try to see, we have this VF. See, VF is nothing but a flow component of velocity. So if I take for an axial flow machine, what will happen? See, VF, okay, VF for an axial flow machine. See, if I take actually in an axial flow machine, it will be its axial component. See, axial flow turbo machine, it will be its axial component. Why it is axial component? That is the direction in which the flow is happening. But what about for a radial flow machine? It is its radial component. The radial flow machine, it will be its radial component. So the flow component in case of an axial flow machine is in the axial direction, and the flow component in case of radial flow machine is in the radial direction. So with this actually, with this background, we should able to go into deriving your Euler or energy transfer equation. Okay. So this is a basic funda. If you have any doubts, so you can unmute and you can speak. That's fine. Hope this is enough for you. This has given enough understanding on the velocity triangles. Are there any doubts? Voice is breaking, that we can't do anything because that may be a network problem. Yeah, any doubts? You can unmute and you can speak. Shall I proceed? I'll discuss on the components, then we'll do the derivation in the next class. Okay. Now, as I told that, we have what is called as the energy transfer. So this is the equation. This is my energy transfer, or it's also called as Euler's energy equation. Okay. Now, hope you all remember you had two types of approaches whenever I'm trying to analyze my fluid flow. One was Lagrangian approach. The second one was an Eulerian approach. Okay. Now, in this kind of a thing, I'm going to use what is called as the control volume. That is Eulerian approach. The control volume. See, the control volume approach, it includes all the blade passages for energy transfer. What is it actually? That means if I go over here, yeah, that means if I try to have blades like this, I have so many blades like this. Okay, so many blades, some 10 blades or whatever it may be. Now, these are the blade passages. I'm trying to show you. These are my blade passages. Okay, these are my blade passages. The fluid is, that means the major thing is the fluid is flowing in between your blades, and that is taken as a control volume. That's the meaning of it. So all the things, here, everywhere I'm trying to take the control volume. So that is means it's a control volume. I'm going to take the fluid is getting filled in the blades. Okay. Then the mass flow rate. See, if that's the case, then I'll go with what is called as, I'm not going the discharge here. So discharge is incompressible. When I'm trying to go with the incompressible fluid, I'll go with the discharge. If I'm going with a compressible fluid, I'll go with mass flow rate, that is m dot is equal to rho into your q. So what is q actually? It is rho into a into your velocity. If I'm dealing with your incompressible fluids actually, then I'm going to deal with your discharge. That is only a into v, because my density doesn't change. Okay. Now, your absolute form, see, one more assumption what I'm going to make is actually here, the absolute velocity, that is v, the absolute velocity almost remains uniform. See, absolute velocity v almost remains uniform, that it does not changing that much. That means there is no too much of fluctuations. There is no too much of fluctuations. And for analysis purpose, I am going to use the conservation of angular momentum. So for analysis of flow, the angular momentum is considered. Angular momentum is, what is this actual angular momentum actually? The rate of change of angular momentum is equal to the torque applied. Shall I write it? So it is the rate of angular momentum is equal to the applied torque. Okay. So with this principles, which are the basic things which are required for us to derive your Euler's energy equation. See, whatever the derivation we are going to do, that particular derivation is same for both your maybe what we call it as axial flow machine or